There are times when the cosmos feels less like a silent expanse and more like a living messenger, and the closing days of September 2025 carried exactly that sense. In a span of hours, two remote stars detonated in titanic outbursts, washing our sector of space with torrents of high-energy radiation. Mere days afterward, comet SWAN ignited with sudden brilliance, its tail unfurling across several degrees of the heavens like a luminous banner. Almost on cue, the sun unleashed a coronal mass ejection, flinging a storm of charged particles toward the comet with a precision that seems to mock ordinary statistics. Yet this is only the overture. Concealed in the star's blinding glare, 3I. Atlas is now racing toward Mars as October 21st draws near, assembling a convergence of electromagnetic forces that may either validate the boldest frontiers of plasma physics or reveal the staggering reach of cosmic coincidence. In the weeks ahead, we will discover whether we are watching an intricate choreography or pure turbulence within the invisible networks of our solar system. Join me tonight as we explore the improbable odds behind these unfolding events and, above all, do not look away from what comes next, for the universe rarely hands us such vivid experiments in its deepest mysteries. Part 1. When the sky exploded 3 times, September 26th, 2025, at precisely 0843 Universal Coordinated Time, the universe delivered what can only be described as a 1-2-3 strike that should leave even the most seasoned astronomers questioning their assumptions about coincidence. Only days earlier, 2 stellar explosions had already ripped through the fabric of space, Nova V 7994 Sagittari and Nova V 1935 Centauri, showering the solar system with torrents of high-energy radiation. Then, almost as if in reply to a signal beyond human comprehension, Comet C 2025 R2 SWAN erupted with sudden intensity. Its magnitude leapt from a steady 6.5 to nearly 5.7 in a matter of hours, while its luminous tail stretched across 2.5 degrees of sky, the equivalent of 5 full moons placed side by side. An enormous arc of ice and dust shimmered against the blackness, as if the comet itself had been awakened by some unseen hand. Yet the universe was not finished composing its dramatic overture. 48 hours later, the sun itself unleashed its own fury. On September 28th, at 0843 Universal Coordinated Time, active region 4232 detonated with an M6.4 class solar flare, the most powerful eruption our star had released in 3 months. The precision of the timing seemed uncanny. The direction of the blast aligned almost perfectly with the orbital path where SWAN was cutting its way through interplanetary space. Any cautious scientist will insist this is nothing more than coincidence. Random events are known to cluster, and the human brain, wired as a pattern-seeking organ, often perceives intentional design in the randomness of swirling clouds or even a bowl of alphabet soup. And yet, sometimes patterns emerge with such startling clarity that even the most skeptical researcher cannot help but pause and wonder whether forces more intricate than chance are at play. Consider the cast assembled in this celestial drama. SWAN had already survived perihelion on September 12th, enduring its closest brush with the Sun and beginning the long return arc toward Earth. By October 20th and 21st, it will make its closest pass to our planet, a mere 0.2606 astronomical units away, roughly 10 million miles. At such proximity, the comet is poised to become one of the most luminous objects gracing the autumn skies of Earth, a blazing torch streaking against the backdrop of stars. Yet SWAN is not the only actor upon the stage. Concealed within the brilliance of the sun's glare, nearly impossible to observe from Earth, drifts a visitor of even greater mystery. 3. Atlas, the third confirmed interstellar object ever to be detected in our solar system, discovered only in July by the Atlas survey team in Chile. This wanderer follows a hyperbolic course that will sweep it past perihelion around October 30th, just inside the orbit of Mars. The geometry of their alignments is almost unnerving in its precision. Both SWAN and Atlas trace their arcs along the ecliptic plane, both immersed within the turbulent folds of the heliospheric current sheet, that vast rippling boundary where the Sun's magnetic field reverses polarity. Both approach their most volatile stages within mere days of each other, all while solar cycle 25 hints at the possibility of entering a more violent phase. As if the universe intended to heighten the spectacle, the new moon of October 21st promises the darkest possible skies, arriving almost to the hour of SWAN's closest passage by Earth. It is as though the cosmos itself has arranged a front-row seat for observers on our planet to witness whatever extraordinary drama is about to unfold. Mainstream space agencies remain steadfast. They remind us that no causal chain has ever been demonstrated linking nova eruptions, cometary outbursts, and solar activity. The United States Geological Survey repeats firmly that earthquake activity on Earth shows no correlation with space weather. These boundaries of accepted science exist for good reason, and they cannot be dismissed lightly. Still, the timing unsettles. The sequence of events feels less like accident and more like choreography, a cosmic score in which energy leaps from one system to another along pathways scarcely understood. Could radiation from distant stellar blasts alter the volatile layers of cometary ice? Could the violent outgassing of a brightening comet nudge the local electromagnetic environment enough to destabilize our own star? Might the Sun's eruptions then ripple outward, affecting planetary magnetospheres in ways we have only begun to suspect? The questions accumulate faster than answers can be tested, but one certainty remains. If this is a grand design rather than the noise of chance, then the decisive beat falls around October 21st. The new moon will shroud Earth in darkness, just as SWAN makes its closest approach, even as 3I Atlas moves unseen behind the solar glare, nearing the height of its solar heating. The trajectory of that coronal mass ejection, the exact angle of its blast, may matter more than any casual observer realizes. Defining what constitutes evidence for electromagnetic feedback between comets and the Sun will require precision, and the week spanning October 19th through 26th may prove decisive. Will the tempo of cosmic violence escalate into a crescendo, or fade into the ordinary hum of background space weather? The stage is fully set, the actors already moving into place. Hidden within the equations of orbital mechanics and the currents of plasma physics lies the answer to whether we are witnessing the most extravagant coincidence of recent astronomical memory or the first glimmer of proof that our solar system functions as a deeply interconnected, electrically resonant machine. The curtain rises on this mystery in just 24 days, and the cosmos itself holds its breath as we await the opening act. Part 2. Comet SWAN's Sudden Awakening. September 26th began much like any other day for comet watchers scattered across the globe. Comet SWAN had been dutifully following its predicted light curve since its discovery, a faint traveler 2 weeks past perihelion, showing the gentle increase and decline of brightness that cometary dynamics usually dictate. Nothing in its behavior hinted that anything unusual was about to happen. Yet in the space of only a few hours, the familiar narrative shifted. Around 0800 Universal Coordinated Time, reports began to emerge from observers in the southern hemisphere. SWAN's coma, previously stable, had erupted with sudden intensity. The comet's magnitude leapt from 6.5 to approximately 5.7, bright enough for the human eye to detect under skies not even fully pristine. It was no longer the faint smudge hidden behind binocular lenses, but an object claiming a place in the theater of naked-eye astronomy. Still, the rise in luminosity was only part of the story. Its tail, once modest and requiring optical aid to appreciate, had transformed into a sweeping streamer spanning 2.5 degrees of the heavens. To place that scale into human perspective, extend your arm and spread your hand. The distance from thumb to pinky finger measures roughly 20 degrees across the sky. SWAN's tail now filled more than 1/8 of that reach, a luminous river of ionized gas and ancient dust cutting across the backdrop of stars. The vision was both ghostly and grand, a silent plume drifting through the void, visible even to those with only modest instruments. For seasoned astronomers, this eruption did not entirely surprise. Comets are volatile by their very nature, fragments of the early solar system preserved in ice and stone, relics older than the planets themselves. Within their nuclei lie the frozen archives of a nebula that condensed 4.5 billion years ago. When sunlight penetrates these fragile bodies, heat stirs hidden reservoirs of carbon monoxide, carbon dioxide, and other hypervolatile compounds. Sublimation follows, and sometimes the pressure of escaping gases shatters the crust, driving outbursts that briefly transform a faint wanderer into a spectacular beacon. SWAN's position on that September morning was particularly sensitive. Having passed perihelion on September 12th, at roughly 1.27 astronomical units from the Sun, the comet was still bathing in significant solar energy. Its orbital path carried it close to the ecliptic plane, the disk along which most planets orbit, and where the Sun's magnetic structures writhe with greatest complexity. This is the arena where physics becomes especially fascinating. The ecliptic harbors the heliospheric current sheet, a vast, undulating membrane where the solar magnetic field reverses polarity. Imagine a ballerina's skirt of unimaginable size, swirling outward from the Sun, rippling at nearly 2 million miles per hour. Within its folds reside magnetic discontinuities, shock fronts, and dense streams of particles. Any body generating plasma that passes through this region becomes a participant in a restless electromagnetic ballet. And comets, surprisingly, are among the most effective plasma creators. As solar radiation frees volatile gases from their icy cores, those molecules are rapidly ionized by ultraviolet photons and buffeted by the solar wind. Around the nucleus grows a coma of charged particles, extending millions of miles, capable of interacting with solar structures long before the solid body itself arrives. What makes a comet's plasma distinct, however, is its cargo of dust. Unlike the relatively clean plasma that swirls around planets, a comet's environment is laden with microscopic grains of silicate, metal, and organic compounds. Plasma physicists call this a dusty plasma, a fourth state of matter in which charged dust alters the dance of ions and electrons. Dusty plasmas resist simple equations, producing nonlinear responses, generating their own fields, and sometimes behaving in ways that challenge the rules of classical magnetohydrodynamics. When SWAN erupted on September 26th, it was not merely brightening. It was evolving into a vast, electrically active structure. The sudden injection of mass, what scientists term mass loading, altered the solar wind locally, disturbing the flow in ways that could send ripples both inward toward the Sun and outward across interplanetary space. Observations confirmed the transformation. Images captured before and after the event showed not only enhanced luminosity, but striking changes in morphology. The ion tail, that slender streamer of charged particles glowing blue-white, became sharper, more articulated. Dust lanes within the coma showed stronger definition. Most intriguingly, the tail's position angle shifted slightly, suggesting fresh jets erupting from new regions of the nucleus. For amateur astronomers in the southern hemisphere, this event offered an unexpected gift. SWAN's southerly position rendered it elusive for northern observers, but across South America, southern Africa, and Australia, stargazers found themselves privileged with a front-row view. Photographs poured onto social media and astronomy forums, documenting in near real time the comet's metamorphosis. What made the spectacle more than a curiosity, however, was its timing. Cometary outbursts are not rare. Comet Hale-Bopp in 1997 produced dozens, each one captivating sky watchers. Comet Lovejoy in 2011, a sun-grazing wanderer, survived a perilous plunge and answered with dramatic jets. Yet SWAN's awakening unfolded against a backdrop of extraordinary cosmic events. Only days earlier, two novae had detonated across the galaxy, releasing unimaginable torrents of energy. In such an eruption, a white dwarf siphons matter from a companion until a runaway thermonuclear flash ignites, hurling photons so powerful they can briefly rival the luminosity of an entire galaxy. The gamma rays and X-rays born in that inferno carry energies measured in millions of electron volts, and though diminished across interstellar gulfs, they still race outward at the speed of light, capable of reaching the inner solar system within days. Could such radiation have tipped the delicate balance within SWAN's nucleus? At Earth's distance, the energy flux from a distant nova is minuscule when set beside the relentless blaze of the sunday, and yet comets are exquisitely sensitive. A subtle addition of heat could awaken a reservoir of frozen gases, coaxing an eruption from a body already under stress. The physics is uncertain, speculative, but the correlation in timing provokes attention. A chain of events begins to take shape in the imagination. Stellar explosions flood our region of space with radiation. Days later, a comet responds with sudden brilliance. Then, as if echoing the crescendo, the sun itself hurls its most powerful flare in months. Perhaps coincidence, perhaps mere clustering of unrelated phenomena, but perhaps also the opening movement of a symphony of energy, resonating through plasma currents that link star, comet, and sun in ways we are only beginning to glimpse. Part 3. The Sun Fires Back. If the universe possesses even the faintest sense of theatrical timing, it displayed that instinct with uncanny precision on September 28th at 0843 Universal Coordinated Time. Exactly 48 hours and 43 minutes after Comet SWAN's mysterious eruption first startled observers, the Sun itself answered with devastating power. From active region 4232, a restless sunspot group brooding on the eastern limb of the solar disk, a sudden explosion ripped across space. The event, classified as an M6.4 solar flare, released in 10 minutes more energy than humanity has generated in all of its history combined. X-ray detectors aboard the geostationary operational environmental satellites recorded the eruption as an R2 radio blackout, powerful enough to disturb high-frequency transmissions across the daylight face of Earth. Yet this flare was merely the overture. Within hours, coronagraph instruments on the Solar and Heliospheric Observatory captured something vastly more ominous: a coronal mass ejection, a billion-ton bubble of magnetized plasma racing outward from the Sun at nearly 2 million miles per hour, a shockwave so immense it dwarfed the scale of planets. The geometry of this blast carried its own subtle drama. Active region 4232, sitting on the Sun's eastern edge, roughly 60 degrees from the direct Earth-Sun line, released its eruption into a corridor of space, intersecting the very orbital plane where SWAN was moving. The ejection spared Earth from a direct strike, but its trajectory suggested that the comet's fragile environment might lie squarely in the path. Understanding how such ejections propagate requires abandoning two-dimensional charts and thinking instead in spirals. The Sun rotates every 27 days, carrying its storm systems across the disk much as jet streams sweep across Earth. When a coronal mass ejection erupts, it does not travel in a straight radial line. Instead, it follows the contorted magnetic scaffolding of the solar wind, winding outward like water arcing from a rotating garden sprinkler. This spiral architecture, known as the interplanetary magnetic field, fills the space between worlds. For SWAN, racing along at nearly 30 kilometers per second, the approaching storm front represented more than a passing disturbance. On that September 28th, the comet was roughly 40 million miles from the Sun, well within the range where the magnetic grip of a coronal ejection retains its coherence and ferocity. If timing aligned, the advancing shock could overtake SWAN within 2 to 3 days, unleashing a direct interaction visible even from Earth. Astronomers have seen such encounters before, and the results can be spectacular. In 2007, Comet Encke provided an unforgettable natural experiment when a coronal mass ejection slammed directly into its ion tail. The stereo spacecraft captured the drama in unprecedented resolution, showing magnetic fields and solar particles severing the tail clean from the nucleus. Within hours, the glowing streamer was gone, swept away like smoke before a storm, while the nucleus, undeterred, continued to pour gas and slowly rebuild what had been destroyed. The physics of these tail disconnections reveals a secret intimacy between comets and the solar wind. A comet's ion tail forms when ultraviolet light from the Sun ionizes gases venting from the coma, charging them so that they lock onto the Sun's magnetic field. Swept backward by the gale of the solar wind, these ions form a straight, spectral ribbon that can extend for millions of miles. When a coronal mass ejection collides with this fragile filament, two possible processes unfold. If the magnetic polarity of the ejection opposes that of the tail, reconnection ignites. Field lines snap and reform violently, severing the tether between nucleus and tail much as auroral storms are born in Earth's skies. Alternatively, the brute ram pressure of the storm's high-velocity plasma may overwhelm the tail's tenuous magnetic bonds, tearing the structure apart, like a hurricane ripping through a veil of mist. In either case, the result is dramatic. The comet's signature plume vanishes within hours, leaving a bare nucleus exposed until fresh outgassing rebuilds the envelope. For SWAN, placed directly in the predicted path of the September 28th ejection, the prospect of such a transformation was real. Observers on Earth would witness sudden changes in the comet's brightness, in the angle of its tail, in the architecture of its coma. Seasoned comet hunters know these moments well, scanning the sky for the telltale signatures of disconnection events whenever solar activity surges. But this encounter carried another question, more subtle and perhaps more profound. The 48-hour delay between SWAN's own eruption and the solar flare from region 4232 matched the range of light travel times from the comet's position to the Sunday. Could SWAN's violent outburst, by dumping a surge of plasma into interplanetary space, have introduced instabilities into the solar corona itself? Mainstream heliophysics insists on caution. The Sun contains 99.86% of all the mass in the solar system, a gravitational and magnetic engine so vast that the energy released by a comet is infinitesimal by comparison. Region 4232 had been accumulating magnetic stress for days, perhaps weeks, and its eruption was statistically inevitable. Yet the precision of the timing unsettles. It suggests correlations that defy easy dismissal. Statistical studies spanning past solar cycles might reveal whether comets and solar flares truly coincide more often than chance allows, or whether the mind's hunger for patterns has simply fooled us again. Defining what constitutes significant correlation across cosmic distances is no small task. What can be measured directly, however, is the ejection itself as it marches outward into the solar system. Models from the Solar Wind Prediction System project the shock front advancing through the inner system by early October, potentially sweeping through the orbital zones, not only of SWAN, but of the enigmatic interstellar visitor known as 3-1 Atlas. The possibility that both a native comet and an alien wanderer could feel the pulse of the same solar storm is compelling, a reminder that our star's influence extends far beyond Earth. For sky watchers, the days following the flare promised rare opportunities. Should SWAN's tail be struck, its disconnection would paint a visible demonstration of the invisible currents that thread the heliosphere. For theorists, the events would test whether the sequence we are watching is nothing more than extraordinary coincidence or the faintest signal of feedback mechanisms binding small icy bodies to the rhythms of the Sunday. As September gave way to October, the stage was set with all the grandeur of celestial theatre. The actors stood in their places, a volatile comet with a luminous plume, a restless star venting its storms, and an interstellar stranger lurking in the wings. The curtain had already risen, and the next act awaited. The question now is whether humanity will recognize the deeper signals in this cosmic performance, or dismiss them as chance alignments in the great electromagnetic web that binds our solar system together. Part 4. The Geometry of Power, October 21st, 2025. Circle this date, because the heavens have arranged a performance that occurs perhaps only once within a human lifetime. On this single day, 3 separate celestial events converge with mathematical precision, so uncanny it might have made ancient skywatchers reach for their most sacred texts. Comet SWAN reaches its closest approach to Earth, a mere 0.2606 astronomical units, roughly 10 million miles, brushing past our planet on a scale vast yet intimately close by cosmic standards. At the same moment, the moon withdraws into its new phase, extinguishing its light and leaving behind the darkest skies possible for observation. And hidden behind the relentless glare of the sun, invisible to ground-based telescopes, the interstellar wanderer known as 3-1 Atlas continues its glide toward perihelion, a passage it will make on October 30th at about 1.4 astronomical units from the solar furnace. This is not mysticism, not the art of astrology, but the strict mathematics of orbital mechanics revealing the deep and silent clockwork that governs our cosmic neighborhood. Yet sometimes orbital mechanics arranges alignments so sharp, so eerily precise, they seem to carry the rhythm of choreography, as though some hidden intelligence had tuned the dance. Both SWAN and Atlas trace paths close to the ecliptic plane, the invisible disk on which Earth and most of the planets orbit. That positioning drops them squarely into the most magnetically charged region of interplanetary space, where the heliospheric current sheet ripples outward like a gigantic skirt of plasma, folding and wrinkling as the sun rotates every 27 days. To understand why this matters is to picture a ballerina's skirt billions of miles wide, its fabric woven not of cloth, but of charged particles and magnetic lines. As the sun spins, the skirt twists, spirals, and bends, creating a living architecture of electromagnetic boundaries. Objects drifting through this environment do not simply obey gravity. They become embedded within the sun's extended electromagnetic field, caught in forces invisible yet potent, forces that can alter behavior in subtle but measurable ways. Comets, with their vast plasma tails and electrically active comae, are especially vulnerable to these conditions. And when more than one large body travels through the same region of this current sheet at nearly the same time, theoretical possibilities arise that science has scarcely explored. Could the combined plasma outpourings from such objects temporarily modify the current density of the heliospheric circuit? Could such disturbances ripple backward toward the Sun itself, destabilizing magnetically charged regions of the corona on the brink of eruption? These questions tread into speculative ground, but they are not without foundation. Each year the solar wind carries nearly 1 billion tons of material outward, an immense loss perfectly balanced by the Sun's gravity and magnetism. Yet when comets dump their own streams of gas and dust into the solar wind, the system must adjust. Imagine, then, the heliospheric current sheet as an immense electrical circuit. The Sun is the generator. The outer boundary of the heliosphere is the load. Comets embedded in this current behave like variable resistors, altering the local flow as they warm or cool along their orbits. Normally, the contribution of any single comet is negligible, lost within the roar of the solar dynamo. But what happens when multiple luminous bodies pour plasma into the same current sheet simultaneously? Could their combined influence create disturbances that propagate at the speed of light, reaching unstable solar regions at exactly the wrong, or perhaps the right moment? Physics urges caution, because the inertia of the solar wind overwhelms cometary contributions by many orders of magnitude. Yet plasma physics is notorious for its nonlinear responses, for the way tiny nudges can trigger avalanches. History offers reminders. The Carrington event of 1859, the most violent geomagnetic storm on record, was triggered not by a uniquely enormous solar eruption but by one that struck when Earth's magnetosphere was in an exquisitely sensitive condition. The result was aurora flaring as far south as the Caribbean and telegraph wires sparking into fire across continents. The lesson is clear. In complex systems, timing matters as much as size. A small input at the critical instant can cascade through the entire system. The October 21st convergence seems designed to test that lesson. The Moon's absence removes interference, offering perfect dark skies for tracking any sudden change in SWAN's tail. The comet's proximity to Earth enhances the sharpness of telescopic imaging, letting astronomers discern delicate structures in its plasma. Meanwhile, Atlas lingers near solar conjunction, invisible to us but dwelling in one of the most electromagnetically active zones of the inner system, precisely when the Sun itself has shown a tendency toward heightened storms. Observationally, this is a gift without precedent. Ground-based telescopes will follow SWAN's tail in detail as it drifts through shock waves and discontinuities in the solar wind. Space-based coronagraphs will record the behavior of Atlas as it undergoes its peak heating near the Sunday together. These observations may reveal not only what happens to comets in turbulent electromagnetic seas, but also whether alignments we call coincidence are instead revealing a hidden resonance within the machinery of the solar system. Probability reminds us that in a cosmos filled with billions of bodies, rare alignments will occasionally occur by chance. The challenge lies in knowing whether this one is simply a statistical curiosity or the unveiling of a deeper principle. If chance rules, then SWAN will behave like many comets before, showing familiar tail disconnections when struck by routine solar storms, nothing beyond what has been documented countless times. But if something more is at work, if SWAN and Atlas together form a resonance condition in which multiple bodies embedded in the same plasma circuit subtly alter the rhythm of the Sun, then we may see correlations that challenge every conventional model of heliophysics. The truth will be revealed only in the data collected across those nights and days. Coronagraph images, plasma readings, ground-based photographs, and magnetic field measurements. From them we will learn whether our solar system is nothing more than a collection of isolated wanderers bound by gravity, or whether it functions as a tightly coupled electromagnetic machine, each component resonating with the others in ways we have scarcely imagined. Either conclusion enriches human understanding. Yet one of them could force us to redefine our place in the cosmos, to recognize ourselves as inhabitants of a universe bound together by invisible threads of energy and timing, a universe perhaps more intricate and interconnected than we ever dared to believe. Part 5. Energy in Motion, from Nova to CME. The sequence unfolds like a cosmic detective story written in the ink of electromagnetic radiation and plasma physics. First come the stellar explosions, two distant novae, unleashing torrents of high-energy photons that sweep through the inner solar system like searchlights. Then a comet, fragile SWAN, suddenly flares with brilliance, erupting in activity as though in answer to some hidden signal. Days later, the sun itself answers with its most powerful flare in months, a solar outburst so perfectly timed that it demands inquiry, even if that inquiry leads us across the thin boundary between speculation and established science. To examine the mystery, we must reconstruct the timeline with forensic care. Nova V 7994 Sagittarii ignited in late September, its thermonuclear flash briefly rivaling thousands of ordinary stars. Only days later, Nova V 1935 Centauri followed, adding its own surge of high-energy radiation to the stream washing across the heliosphere. Both were unmistakable, captured by gamma-ray and X-ray observatories that confirmed these were not modest stellar flares but true novae. White dwarf stars siphoning matter from companions until critical density unleashed runaway fusion. The power involved dwarfs' comprehension. In mere hours, such explosions release more energy than our sun will radiate across millions of years. Each photon carried millions of times the energy of visible light, sufficient to ionize atoms and drive chemical changes across distances that defy imagination. When these photons reached the inner solar system, racing at light speed, they encountered the mixed company of planets, asteroids, comets, and the sun itself. For most objects, the added flux was negligible beside the ordinary blaze of solar irradiation. But comets, with their raw surfaces and volatile cores, stand as sensitive receivers, primed to respond to even minor perturbations in their thermal balance. Conservative physics tells a firm story. Fluxes from novae are minuscule compared to sunlight, their intensities diluted by thousands of light-years of space. To propose a direct causal link between distant nova radiation and SWAN's September 26th eruption requires new mechanisms, ones not encompassed by current models of how radiation interacts with cometary matter. Yet the uncanny alignment of timing whispers for consideration. Might high-energy photons trigger processes beneath cometary crusts, beyond the reach of simple radiative heating? Gamma rays and X-rays can burrow far deeper into solid material than visible light, reaching strata where exotic volatiles lie dormant. Conceivably, such penetration could warm hidden reservoirs, building pressures that burst forth in explosive jets. Thus emerges the speculative energetic chain hypothesis. In this narrative, nova photons perturb subsurface chemistry of comets across the inner system. This awakens outgassing, generating larger plasma envelopes. The surge of material alters mass loading in the solar wind and changes conditions in the heliospheric current sheet. Disturbances then ripple back toward the sun, arriving at vulnerable magnetic regions already near instability. Under just the right timing, those instabilities break, producing solar flares or coronal ejections. Each link in this chain is fraught with obstacles. Nova radiation diminishes brutally with distance, leaving scarcely any measurable increment at cometary orbits. Cometary outbursts are overwhelmingly governed by direct solar heating, which dominates any external source. The total mass comets contribute to the solar wind is vanishingly small beside the billion tons the Sun itself releases each year, and the evolution of active regions follows its own labyrinth of magnetic stresses that appear indifferent to such tiny perturbations. To test the hypothesis requires strategies capable of distinguishing real coupling from the illusion of pattern produced by coincidental timing. If nova-comet-sun coupling is genuine, then repeatable signatures should appear across multiple events. What would falsify the chain? If SWAN's outburst began before nova peaks reached the inner system, causality collapses. If future solar eruptions show no temporal correlation with comet positions, the connection falters. If spacecraft sampling the solar wind register no anomalies when supposed electromagnetic linkages are predicted, the mechanism evaporates. Historical records offer another proving ground. Across the last 2 solar cycles, astronomers have catalogued dozens of nova detonations, hundreds of cometary outbursts, thousands of solar flares and ejections. If energetic chains truly operate, then statistical analysis should uncover biases in timing that rise above chance. Yet this is perilous ground. Comets erupt for many reasons: rotational stresses, seasonal illumination, impact with debris, or stochastic variations in sublimation. Solar flares arise from complex magnetic knots that evolve independently of cometary antics. Novae occur far beyond the solar system according to the physics of accreting binaries, utterly disconnected from planetary circumstances. To draw lines between such disparate domains demands great caution. Human perception is itself the most treacherous variable. Our brains are exquisite at detecting patterns, even in noise, especially when the patterns support grand narratives of cosmic unity. It is tempting to see harmony where none exists, to weave stories of synchronous orchestration out of mere statistical clustering. Yet to dismiss the September chain as coincidence alone may be equally rash. Scientific progress has always depended on entertaining strange correlations while subjecting them to ruthless testing. The path forward lies not in uncritical acceptance nor cynical rejection, but in the discipline of prediction. If the energetic chain exists, then future alignments should produce measurable echoes. New comets should exhibit outbursts that follow nova pulses. Solar regions should flare with greater frequency when comets traverse current sheet boundaries freshly disturbed. Data from SWAN's continuing approach and from the enigmatic interstellar visitor 3I Atlas approaching perihelion provide a near-term chance to test the idea. In the weeks ahead, telescopes, satellites, and coronagraphs will gather records. Those records may prove the chain an illusion born of timing, or they may reveal subtle couplings overlooked by orthodox theory. Either way, we confront the same truth. The universe has presented us with a puzzle of profound intrigue. Its solution requires observation as meticulous as any forensic inquiry, analysis as rigorous as any courtroom argument, and above all, the intellectual honesty to recognize both the seduction of cosmic synchronicity and the unforgiving demands of evidence. Perhaps the pattern is nothing more than coincidence, an accidental rhythm in the vast music of space. Or perhaps it is the faint overtone of a deeper structure, one that hints our solar system is woven into larger networks of energy than we have yet dared to imagine. Part 6. The Plasma Bridge Hypothesis. Buried deep within the mathematics of plasma physics lies a possibility so elegant and so unsettling that mainstream heliophysics has largely set it aside for decades. The idea proposes that comets are not merely passive lumps of ice and rock heated by the sun's radiation, but rather transient electrodes in a vast solar system circuit. capable of modulating electromagnetic flows across millions of miles of interplanetary space. This vision is known as the plasma bridge hypothesis, and its ancestry stretches back to the pioneering insights of Hannes Alfvén, the Swedish physicist who earned the Nobel Prize for developing the foundations of magnetohydrodynamics. Alfvén's revolutionary perspective was that space is not empty, but saturated with charged particles, magnetic fields, and currents flowing silently across astronomical distances. In his conception, the solar system resembles an immense electrical circuit. The sun is the generator, producing streams of charged particles and embedded magnetic fields that pour outward at nearly 2 million miles per hour. This solar wind carries electrical currents linking the sun to planets, asteroids, comets, and the distant boundary of interstellar space some 11 billion miles away. Most bodies act as passive loads in this circuit, absorbing energy without altering its course. Yet Alfvén suspected comets might be different. Their volatile nuclei can suddenly erupt with jets of gas and plasma, altering the electrical properties of their surroundings, creating feedback loops that could ripple across the heliosphere. The key mechanism is what plasma physicists call double layers, regions where positive and negative charges separate and generate intense electric fields. Such structures can accelerate particles, ignite currents, and behave as natural accelerators in the vacuum of space. When a comet erupts and fills its coma with dense plasma, these double layers may organize themselves, coupling the comet to solar currents in complex, non-linear ways. Unlike the relatively clean plasma of planetary magnetospheres, a comet's environment is loaded with dust. Solar photons and wind charge these grains, transforming the comet's atmosphere into a dusty plasma, a fourth state of matter where microscopic particles carry charges strong enough to reshape the motions of ions and electrons. Dusty plasmas are remarkable for their self-organizing behavior, capable of forming spirals, waves, even cellular patterns reminiscent of living networks. Laboratory experiments show them generating fields, sustaining coherent structures, and defying simple fluid models. Transpose these behaviors to cometary scales, and one can imagine outbursting nuclei, creating temporary plasma structures capable of interacting with solar currents in surprising ways. The hypothesis gains further weight when considered alongside the heliospheric current sheet, the sprawling boundary where the sun's magnetic polarity reverses. This sheet, rippling outward like a ballerina's skirt of plasma, is the solar system's most electrically active zone. Magnetic fields reconnect here, particle flows accelerate, and charge domains reorganize on colossal scales. Comets traversing such terrain experience abrupt electromagnetic changes that can whip their tails into new forms or trigger disconnection events. SWAN's orbit, lying close to the ecliptic, ensures repeated encounters with this current sheet. When it outburst on September 26th, its transformation may have gone beyond a mere brightening. It could have acted, if only for hours or days, as a temporary electrode altering local current flows in ways that could, in theory, ripple back toward the sun itself. Testing such a claim requires demanding evidence. True electromagnetic coupling would leave fingerprints in particle spectra, in radio emissions, in magnetic field measurements. One would expect correlations between comet outbursts and solar flares that repeat across events and across cycles, particularly when comets skirt the current sheet. Yet our observational tools are sparse. We lack plasma probes near SWAN, forced instead to rely on remote imaging and numerical models. Missions like Parker Solar Probe furnish exquisite detail about the solar wind near Earth, but extending those measurements outward to cometary distances multiplies uncertainty. history does supply vivid examples of one-way interactions. In 2007, a coronal mass ejection struck Comet Encke, severing its ion tail in a matter of hours. Stereo spacecraft watched magnetic reconnection reconfigure the comet's environment dramatically, an unambiguous demonstration of how the sun can reshape a comet. But in that story, causality ran only outward from sun to comet. The reverse, the idea that comets can feed back and influence solar activity, remains a tantalizing speculation. Still, the plasma bridge hypothesis dares to sketch predictions. If SWAN and the interstellar visitor 3I Atlas possess the ability to couple electromagnetically with the Sun, then during their October convergence, we might detect correlations between their activity and solar flares that rise above random coincidence. Radio telescopes could hear coherent emissions signaling current flows along invisible bridges. Particle detectors might find energetic populations traceable to cometary origins, or we may find nothing at all. The energy scales of the Sun are vast, dwarfing cometary contributions by orders of magnitude. In such a view, comets are sparks in a hurricane, incapable of altering the storm. Their apparent correlations with solar activity are coincidences amplified by human pattern-seeking minds. But should evidence emerge to support plasma bridges, the implications would be profound. We would no longer see our solar system as a simple collection of isolated bodies orbiting a central furnace, but as a living circuit where currents, information, and feedback flow in both directions between star and satellites. The coming weeks will test this vision. SWAN brightens as it nears Earth. Atlas approaches perihelion, and the Sun seethes with magnetic tension. Observers will watch for correlations, for signals, for evidence of hidden currents. Perhaps the bridges exist, unseen but real, threads of plasma knitting comets into the heart of the solar machine. Or perhaps the patterns dissolve into noise, leaving only the enduring lesson that science must follow evidence rather than desire. In either case, our knowledge deepens, and the cosmic detective story continues, reminding us that the universe often hides its deepest truths within the interplay of timing, coincidence, and the relentless search for connection. Part 7. The historical precedent, Oumuamua, and the 2017 Mexico quake. Sometimes the universe arranges its events with such uncannily precise timing that even the most skeptical voices in science hesitate, caught between rational explanation and the nagging suspicion that coincidence alone might not suffice. September of 2017 delivered one such sequence, a convergence of solar violence and terrestrial catastrophe that continues to echo in debates about cause and effect across the solar system. The story began on September 6th, when the Sun unleashed an X9.3 solar flare, one of the most powerful eruptions ever recorded in the modern era. The blast expelled a vast coronal mass ejection, racing toward Earth at more than 4 million miles per hour. Within days, geomagnetic storms battered the magnetosphere, and auroral curtains shimmered as far south as Alabama, painting skies with electric fire rarely seen outside the polar zones. Yet this was only the opening movement in a cosmic composition of unnerving symmetry. 3 days later, on September 9th, the first known interstellar visitor revealed its closest embrace with the Sunday Oumuamua, a spindle-shaped wanderer that had traversed the gulfs between stars for millions of years, swept past perihelion at a distance of roughly 25 million miles, closer than Mercury's orbit. Its tumbling trajectory and elongated shape set it apart from any asteroid or comet catalogued before, proof that fragments of alien systems do drift into our own. The timing might have seemed striking enough, but the Sun was not yet finished. On September 10th, scarcely 24 hours after Oumuamua's closest solar pass, another titanic eruption flared from the star. This time, it was classified as X8.2, the second most powerful solar detonation of the entire cycle. The back-to-back outbursts produced a prolonged storm of radiation and particles, flooding Earth's magnetic shield for days and straining communications and satellites. And then, as if the tremors of space had whispered to the planet itself, Earth shook. On September 8th, almost precisely midway between the two great flares, and coinciding to the day with Oumuamua's perihelion, a magnitude 8.2 earthquake struck the isthmus of Tehuantepec in southern Mexico. The rupture, centered near the town of Pijijiapan in Chiapas state, unleashed tsunami warnings across the Pacific and was felt nearly 400 miles away in Mexico City, where buildings swayed and streets filled with frightened crowds. The statistical unlikelihood of such clustering is hard to exaggerate. Earthquakes greater than magnitude 8 occur on average perhaps once a year across the globe. X-class solar flares, the most violent category, appear only a handful of times in an 11-year cycle. Interstellar bodies approach perihelion in our solar system maybe once in a human lifetime. For all three phenomena to align within a 4-day span seems, by the rules of probability, nearly impossible, and yet it happened. The United States Geological Survey, however, maintains a steadfast position. No evidence exists for a causal bridge between solar storms and seismic ruptures. Earthquakes, the agency affirms, are the result of tectonic stress accumulated over centuries, released suddenly along fractures in Earth's crust as plates grind, collide, and shift. Solar flares and geomagnetic storms, though disruptive to satellites and power grids, have no mechanism for driving motion along geological faults. This conclusion rests on decades of statistical scrutiny, where thousands of earthquakes across multiple solar cycles have been tested against records of solar activity, geomagnetic indices, and cosmic ray variations. The overwhelming result shows no consistent pattern. To the mainstream eye, the September sequence remains nothing more than coincidence. Yet beyond the orthodoxy, alternative lines of research continue to probe the fringes of possibility. A growing body of studies, some published in peer-reviewed journals, describe subtle correlations between disturbances in the atmosphere or ionosphere and the timing of earthquakes. These models of lithosphere, atmosphere, ionosphere coupling propose that electrical and electromagnetic processes could influence seismic activity in ways not fully recognized. The theory suggests that as rocks in stressed faults accumulate strain, they may also accumulate electrical charge. This charge, building invisibly within the lithosphere, could leak upward, creating electromagnetic anomalies detectable in the atmosphere and ionosphere above. Indeed, satellites have recorded strange emissions and perturbations in ionospheric layers, hours or even days before certain major quakes. If such precursors are genuine, then the reverse possibility must also be considered. External electromagnetic disturbances, whether from solar storms or cosmic radiation, might in rare cases tip stressed faults toward failure. For most seismologists, these ideas remain speculative, constrained by limited data and the need for far stronger predictive evidence. Yet they illustrate why the September 2017 sequence continues to haunt discussion. It embodies the tension between orthodox science, which insists on geological independence, and the human instinct to search for connection in cosmic patterns. The truth may ultimately reinforce conventional wisdom, but the timing, so eerily exact, ensures that the debate will not soon be forgotten. If such coupling mechanisms truly exist, then periods of intense geomagnetic activity, such as those unleashed by X-class solar flares, could in theory alter the electrical state of Earth's upper atmosphere and ionosphere in ways subtle, yet capable of influencing seismic processes. The energy scales pose an obvious problem for direct causation, but complex systems often harbor thresholds where the smallest input, if applied at precisely the right instant, can tip the balance and trigger cascading responses. The Mexico sequence of 2017 stands as a natural experiment in this regard. The devastating earthquake in the Tehuantepec region erupted along a fault where the Cocos Plate steadily grinds beneath the North American plate, a tectonic boundary primed with stress that had been accumulating for decades. A major rupture was statistically inevitable within any given year, but the question remains whether the intense space weather surrounding Oumuamua's perihelion might have influenced the exact timing of that release. To probe such a question requires a forensic layering of evidence. Ionospheric measurements from the days preceding the quake would need to be scrutinized for anomalies aligning with the flare activity. Ground-based magnetometers might reveal signatures of heightened electromagnetic disturbance across the region of tectonic stress. Broader statistical studies comparing global seismicity with other episodes of extreme space weather could help establish whether the Mexican event was a meaningful correlation or nothing more than a cosmic coincidence. Yet the challenge lies in disentangling genuine physics from the illusions conjured by human pattern-seeking minds. Large earthquakes are unforgettable. They dominate headlines and linger in memory, while the countless smaller tremors that occur every day slip quietly into obscurity. Likewise, spectacular solar flares draw disproportionate attention because they produce visible aurora, disrupt satellites, and dominate media cycles, making them seem more frequent and more consequential than the quiet background of solar behavior. When dramatic events cluster in time, the instinct is to weave them into a causal story, even when the underlying processes may be unrelated. Science guards against such false correlations with rigorous statistics, correcting for multiple comparisons and selection biases that make chance alignments appear significant. Yet completely dismissing the September 2017 sequence as mere coincidence may also be premature. Progress has always depended on treating intriguing correlations seriously, subjecting them to critical scrutiny while resisting the lure of premature certainty. The alignment of an interstellar visitor, solar extremes, and a major seismic rupture provides a rare case study for exploring the possibility of electromagnetic coupling between cosmic and terrestrial domains. As October 2025 approaches, bringing with it the convergence of comet SWAN, the interstellar wanderer 3I Atlas, and heightened solar activity, the lessons of 2017 remain both cautionary and inspiring. If genuine coupling exists, if energy flows between stars, comets, magnetic fields, and the restless crust of our planet, then we might expect to see echoes of that pattern repeat under comparable conditions. The coming weeks will serve as a crucible for testing such ideas, a chance to discern whether the Mexican earthquake represents a profound example of hidden physics or simply the kind of chance clustering that tempts even the most disciplined among us toward conspiracy. Either way, the outcome enriches our understanding of how energy and information move across the invisible threads, binding the cosmos to the fragile sphere we call home. Part 8. The Forgotten Solar Mysteries. Hidden within the archives of space-based observations are encounters so dramatic they altered our understanding of solar and cometary physics, yet they faded quietly from public memory as newer discoveries claimed the headlines. These forgotten episodes reveal the sun's capacity for astonishing precision in its violence and provide critical context for grasping what may unfold as the celestial alignments of October draw near. Among the most extraordinary of these events was Comet Encke's unforgettable meeting with a coronal mass ejection in the year 2007. The stereo spacecraft, placed to deliver stereoscopic views of the Sun's corona, recorded the entire spectacle in exquisite detail as a billion-ton sphere of magnetized plasma, racing at nearly 3 million miles per hour, slammed into Encke's fragile ion tail and tore it apart in a matter of hours. The sequence began innocently enough. Encke, a short-period comet returning to the inner solar system every 3.3 years, was approaching perihelion and showing off the familiar blue-white streamer of charged particles that forms when solar ultraviolet radiation ionizes gases boiling from the nucleus. The tail, composed mostly of carbon monoxide and water vapor ions, stretched for millions of miles, tracing the coupling of the comet's plasma to the Sun's sprawling magnetic field. Then the coronal mass ejection arrived with surgical accuracy. Stereo's cameras documented the instant of impact, when the shock front, essentially a moving wall of magnetized plasma faster than the speed of sound in the solar wind, engulfed the comet's delicate structure. Within mere hours, magnetic reconnection had cut the tether between nucleus and tail, leaving a spectral streamer of ionized gas adrift, quickly swept away by the intensified solar wind. Yet Encke's nucleus endured, continuing to vent new gas and dust, gradually assembling a replacement tail. Time-lapse imagery showed the ethereal plume rebuilding itself day by day, rising like a phoenix from electromagnetic ashes. The episode delivered irrefutable proof that solar storms can reorganize cometary plasma structures through direct electromagnetic interaction. 7 years later, another encounter would push the lesson even further. Comet Siding Spring, a visitor from the Oort cloud following a million-year orbit, plunged inward and brushed past Mars in 2014 at a distance of only 87,000 miles. Its vast coma enveloped the red planet, triggering the most intense meteor shower in Martian history. NASA's MAVEN spacecraft, orbiting Mars to study its upper atmosphere, suddenly found itself flying through the comet's extended shroud while its instruments monitored the planetary response. What it observed exceeded all predictions. Dust and gas from Siding Spring flooded the Martian sky, seeding metallic ions into the ionosphere and generating disturbances that lingered for days. The energy input heated Mars's tenuous upper atmosphere by several hundred degrees, a dramatic demonstration that comets, even fleeting visitors, can meaningfully alter planetary systems. If a comet could so transform the thin air of Mars, the implications for their ability to interact with the magnetically charged Sun became impossible to ignore. These episodes remind us that comets are far more than passive relics of the solar nebula. They are dynamic, electrically active travelers capable of reshaping their environments and the worlds they encounter. Once embedded within the solar wind, and especially within the heliospheric current sheet, outgassing comets act as temporary plasma sources, locally reorganizing field lines and particle flows over vast distances. The metaphor of comets as conductive probes dipping into and sampling the electrical state of interplanetary space may be speculative, but it offers a compelling framework. As they traverse regions of shifting magnetic polarity, comets experience environments that change their plasma production, alter their tail morphology, and perhaps influence current flow patterns in ways that could, under certain conditions, propagate back toward the Sunday mainstream heliophysics rightly counsels caution. The scale of energy within the solar corona dwarfs anything a comet can provide. The Sun's magnetic field contains power enough to fuel human civilization for millions of years, while even the most massive comet contributes only a whisper of plasma in comparison. Yet plasma physics is infamous for nonlinear thresholds, for systems that remain stable until the smallest nudge triggers dramatic cascades. Active regions in the solar atmosphere can spend days or weeks storing tension, poised on the verge of eruption. During such critical build-up phases, perhaps even a subtle perturbation could be enough to unleash a flare or coronal mass ejection, just as a small vibration can trigger a catastrophic avalanche when a mountain slope is already unstable. To test such possibilities requires careful strategies. Coordinated campaigns must track comet positions, monitor their activity, and compare plasma properties against the timing of solar eruptions. Statistical studies across many events will be needed to decide whether correlations exceed random chance. The October convergence of comet SWAN nearing Earth and the interstellar wanderer 3-1 Atlas reaching perihelion near the Sun provides a rare opportunity. If electromagnetic coupling between comets and solar activity is real, then the geometry and timing of this alignment should produce detectable signatures in the space weather record, shifts in particle spectra, anomalies in magnetic field measurements, or perhaps coherent radio emissions linking cometary plasma with solar disturbances. Alternatively, the alignment may produce nothing beyond ordinary cometary behavior, sculpted by routine solar wind variations. Either result will sharpen our knowledge. Yet if comet-to-sun feedback is demonstrated, it will demand a profound rethinking of the solar system as an interconnected circuit, rather than a collection of isolated actors. The forgotten dramas of Encke's disconnection and Siding Spring's planetary storm stand as reminders. They tell us that cosmic interactions often exceed the boundaries of conventional expectation and that the universe holds surprises for those willing to look with fresh eyes. As October approaches and comets cross paths with solar turbulence, we may be poised to witness another chapter in this continuing saga of electromagnetic entanglement, a drama played out not on human scales, but across the vast and intricate stage of interplanetary space. Part 9. The Nova-Solar Coupling Theory. Few phenomena release energy on scales so immense that they dwarf the human imagination as completely as nova explosions. When a white dwarf star accumulates enough stolen material from its companion to ignite runaway thermonuclear fusion on its surface, the resulting detonation can for a brief span outshine an entire galaxy, pouring torrents of high-energy radiation into surrounding space. Such radiation races outward at the speed of light, crossing interstellar distances with ease, and in late September of 2025, two separate novae V 7994 Sagittarii and V 1935 Centauri unleashed precisely this kind of cosmic violence. Their emissions were recorded by gamma-ray and X-ray observatories, confirming their authenticity and marking the arrival of their high-energy signals at Earth, at Brutha, and across the inner solar system only days after the initial eruptions. The coincidence in timing was impossible to ignore. The photon streams arrived just before Comet SWAN's sudden outburst and the solar flare that soon followed, a sequence so tightly aligned that it compels investigation, even if that inquiry wanders into speculative terrain. The skeptical case against nova-to-sun coupling is undeniably strong. Energy flux from such distant detonations, though gargantuan in total, becomes dispersed across incomprehensibly vast volumes of space before reaching our system. By the time it arrives at Earth, even the brightest nova delivers an energy density billions of times weaker than ordinary sunlight. The combined output of both September novae, integrated across their entire active phases, would barely be sufficient to power a household lamp for a handful of seconds. To suggest that such feeble increments could provoke a solar flare, a phenomenon that liberates more energy than all of human history's accomplishments combined, seems to violate the most basic sense of scale. Yet complex systems are notorious for defying linear expectations. The real question is not whether nova photons carry enough raw power to force the sun into eruption, but whether they might influence already unstable configurations at delicate moments. Solar active regions can simmer for days or weeks, magnetic energy twisting into ever tighter knots through plasma flows, field line evolution, and thermal dynamics. During such marginally stable periods, even the smallest disturbance could in theory advance or delay the timing of a flare that was destined to occur regardless. High-energy photons differ in their physical behavior from ordinary sunlight. Gamma rays and X-rays can penetrate far more deeply into both plasma and solid matter, reaching layers where unusual interactions dominate. In the corona, these photons might subtly affect ionization balances, alter heating rates, or influence magnetic reconnection processes in ways that our current models, tuned primarily to local solar heating, have yet to capture. At the edges of theory lie even stranger possibilities. Some researchers have wondered whether the flood of neutrinos produced in thermonuclear detonations might, under conditions poorly understood, interact with solar plasma in ways our models cannot predict. Others imagine that high-energy photons might set off cascades of secondary particles, amplifying small perturbations into larger effects. The obstacles facing these ideas are immense. Neutrinos have such vanishingly small cross-sections that trillions pass through every human body each second without noticeable effect. The likelihood of neutrinos from novae thousands of light-years away measurably altering solar plasma is effectively nil within current physics. Yet dismissing every possibility risks overlooking how non-linear systems sometimes surprise us. A more modest explanation may lie not in physical influence, but in the illusions of synchrony. Human perception is wired to notice patterns, and when dramatic events align, we are quick to weave them into a causal chain. Solar rotation imposes 27-day cycles on active region visibility. The heliospheric current sheet oscillates with similar periodicities. Cometary orbits dictate predictable moments of brightness and perihelion. Even observational conditions tied to Earth's own orbit create recurring patterns. When multiple independent oscillators are overlaid, apparent synchronizations are mathematically inevitable. The challenge, then, is distinguishing true causation from the coincidence produced by interacting cycles. To test the idea rigorously, researchers would need to compile an exhaustive catalogue of nova explosions spanning decades, noting their exact dates, distances, and energy yields. This database would be compared to records of solar flares, searching for correlations that exceed random chance after correcting for multiple comparisons. Because dramatic events like X-class flares or unusually bright comets dominate human memory, while less remarkable occurrences fade from recollection, careful statistical control is essential. Monte Carlo simulations, generating thousands of random timelines based on real astronomical distributions, could provide a baseline for judging whether any observed clustering is truly anomalous. Such tests would cut through the bias of selective attention and reveal whether nova-to-sun coincidences are real or simply the inevitable mathematics of randomness. For now, the verdict must remain provisional. The energy scales argue persuasively against direct causation, yet the behavior of complex systems invites humility. Small inputs can under rare conditions precipitate immense outcomes, provided the system is already poised at the brink. As October approaches, with comet SWAN nearing Earth, the interstellar traveler 3I Atlas sweeping toward perihelion, and the sun stirring with fresh magnetic energy, the solar system offers a natural laboratory for testing these hypotheses. If nova radiation truly exerts influence, we may see echoes of September's sequence repeat. If not, the alignment will fade into the catalogue of striking coincidences that pepper astronomical history. Either way, our understanding advances. Perhaps the September novae represent the first chords of a larger cosmic symphony, subtle signals cascading across interstellar distances to play upon the strings of our star. Or perhaps they serve only as a reminder that in a universe with billions of energetic objects, the improbable becomes inevitable, and what feels orchestrated may be nothing more than the relentless rhythm of chance. Part 10. Three-Eye Atlas. The enigma behind the Sunday. Somewhere deep in the glare of our star, hidden from the reach of Earth-based telescopes, moves an object that challenges much of what we thought we understood about wanderers from interstellar space. Three-Eye Atlas, the third confirmed interstellar visitor ever detected, was first observed on the 1st of July in the year 2025 by the Asteroid Terrestrial Impact Last Alert System survey in Chile. From the instant of its discovery, it has stood apart as one of the most mysterious and potentially significant astronomical finds of the 21st century. Its predecessors had already astonished the scientific world. The elongated, tumbling asteroid, Oumuamua, first seen in 2017, and the more comet-like Two-Eye Borisov, which swept through the solar system in 2019. But Three-Eye Atlas follows a distinctly hyperbolic trajectory, carrying it toward a fiery perihelion on the 30th of October at roughly 1.4 astronomical units from the Sunday. That distance places it just inside the orbit of Mars at its closest pass, making it the nearest interstellar object ever observed during a solar encounter. The geometry of its current position creates both remarkable opportunities and severe challenges for those seeking to study it. Through September and into early October, the object maintains an extremely low solar elongation as seen from Earth, meaning it hovers perilously close to the Sun's position in our skies. Such alignment makes direct observation nearly impossible for ground-based instruments, requiring coronagraphs or spaceborne observatories capable of suppressing the solar glare. Yet what Three-Eye Atlas withholds from earthly eyes, it yields to other watchers. Orbiters around Mars, positioned at just the right vantage point, now find themselves with a unique opportunity to study this visitor from the stars as it draws nearer to the Sunday. The European Space Agency has already announced that several of its Mars and Jupiter missions are being tasked to monitor Three-Eye Atlas during its solar encounter, raising the possibility of obtaining data never before captured about an interstellar body navigating the inner system. Calculations predict the object's closest pass to Mars will occur around the 3rd of October, when it will come within approximately 30 million kilometers, or about 0.19 astronomical units of the red planet. Though such a span is immense in human terms, it places the comet within striking range of Mars-based instruments capable of conducting spectroscopic analysis, monitoring dust, and searching for the faint glow of any coma or outgassing activity as solar heating reaches its peak. Early glimpses of Three-Eye Atlas suggest it may already be developing a more substantial coma than Two-Eye Borisov ever exhibited during its passage in 2019. Preliminary reports hint at activity reminiscent of a true comet rather than a barren asteroid, though the low elongation makes these observations uncertain and difficult to confirm. Still, the mere possibility has stirred imaginations. Some researchers speak of the hidden colossus hypothesis, speculation that the object may harbor large reserves of hypervolatile compounds, such as carbon monoxide or nitrogen, substances that vaporize readily even far from the Sunday. If true, then as it nears perihelion, the object could release vast quantities of gas and dust, generating a coma that stretches millions of miles, a structure massive enough to impede the flow of the solar wind and inject substantial plasma into the inner heliosphere. The physics of such an encounter drifts into largely uncharted waters. Previous interstellar visitors were small, faint, and only modestly active, offering little chance to study their effect on the surrounding solar wind. But if 3I Atlas proves richer in volatiles, it could furnish the first opportunity to observe how material from beyond our system interacts with, and perhaps even modifies, the plasma environment generated by our Sunday. The idea has inspired metaphors of interstellar capacitors, objects carrying with them the electromagnetic heritage of deep space. Interstellar space is not empty. It is filled with its own magnetic fields, cosmic ray fluxes, and plasma densities distinct from the domain dominated by the solar wind. A body entering the heliosphere might carry signatures of those external conditions in its magnetic and electrical properties. If so, then its meeting with the Sun could reveal information about environments far beyond the heliopause. To test such possibilities requires instrumentation both precise and imaginative. Spectroscopic analysis could uncover the composition of its coma, especially the fingerprints of hypervolatile gases that sublime under modest heating. Polarimetric observations could measure dust properties and particle distributions unlike those of familiar solar system bodies. Radio arrays might even detect coherent emissions generated by plasma interactions between the interstellar traveler and the solar wind. The difficulty, as always, is to separate genuine physical signals from noise, artifacts, and the limitations of instrumentation. The object's low elongation presents enormous barriers for Earth-based telescopes, while even spaceborne platforms capable of looking near the Sun have only narrow windows for such measurements. Agencies therefore remain cautious. NASA's public position stresses the need for peer-reviewed confirmation before making bold claims. Early reports in popular media have already exaggerated estimates of size, activity, and even potential hazards, highlighting how little we truly know. The most immediate and testable evidence may come not from images but from orbital dynamics. Interstellar comets often betray their activity through subtle non-gravitational accelerations, tiny deviations in their trajectory as jets of gas exert thrust on the nucleus. Both Oumuamua and Borisov exhibited such signatures. If 3I Atlas shows similar behavior, it will strengthen the case that it is a volatile, rich, active body rather than a barren fragment. The European Space Agency's decision to direct multiple spacecraft toward this encounter underscores its significance. Mars Express, the ExoMars Trace Gas Orbiter, and even the Jupiter Icy Moons Explorer could contribute coordinated data as the object whips through its perihelion passage. Such collaboration might at last yield the first detailed dataset on how an interstellar body behaves during maximum solar heating. And as fate would have it, the timing coincides with comet SWAN's closest approach to Earth, setting the stage for a cosmic duet between two very different wanderers. One a long-period comet of our own system, the other a visitor from the stars. Whether this synchrony carries physical meaning or stands as mere coincidence, the weeks ahead promise to expand our knowledge. The enigma hidden in the solar glare may yet reveal truths not only about how alien matter reacts within our heliosphere, but also about the larger flows of plasma, dust, and energy that thread our galaxy. In its shadowed approach lies the possibility of discovery, the chance to glimpse how the universe beyond the Sun's dominion leaves its mark upon the fragile boundary of our cosmic neighborhood. Part 11. Solar Cycle 25 reaches a breaking point. The Sun is awakening, and it is doing so with a ferocity that has startled even the most seasoned solar physicists. Solar Cycle 25, which began officially in December of 2019, has already surpassed nearly every forecast and continues to rise toward what may prove one of the most active solar maxima in living memory. When the prediction panel convened in 2019 to issue its long-range outlook, the consensus was cautious. They projected a relatively weak cycle, estimating a maximum sunspot number of around 115, not much different from the disappointing performance of the previous cycle. But our star had other plans. By 2023, it became undeniable that solar activity was racing far ahead of schedule. Sunspot counts exceeded expectations, flare rates rose steadily, and coronal mass ejections erupted with a frequency and intensity that defied the modest predictions. The eruption of an M6.4 flare on the 28th of September from active region 4232 was only the latest evidence that this cycle is climbing toward a crescendo. M-class flares are common once solar maximum arrives, but the persistence and strength of recent activity suggest that solar cycle 25 could rival some of the most dramatic space weather episodes in recorded history. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center keeps constant watch, employing multiple indices to build a comprehensive portrait of the Sun's electromagnetic state. The F10.7 solar flux, a radio emission that serves as a reliable proxy for overall solar activity, has remained elevated through 2024 and deep into 2025. At the same time, X-ray flux levels recorded by the geostationary operational environmental satellites have shown a sustained rise in background emissions, a sign that coronal heating is intensified across multiple regions of the solar atmosphere. Perhaps most telling of all, the rate of Earth-directed coronal mass ejections has risen sharply in the past year. Each of these billion-ton plasma clouds, when hurled toward our planet, has the potential to rattle the magnetosphere, disrupt communications, ignite auroras, and in extreme cases, induce currents powerful enough to threaten modern power grids. The physics driving this intensification lies in the interplay of magnetic fields and plasma flows. Energy forged in the nuclear furnace at the solar core migrates outward, carried by convective motions until it reaches the visible surface. Active regions emerge, where twisted magnetic field lines pierce the photosphere, forming the dark sunspots seen in telescopes. These fields twist and shear as plasma flows carry them along, winding them into unstable knots. When the tension grows too great, reconnection occurs, unleashing vast reservoirs of magnetic energy as solar flares and coronal mass ejections. The energy released is almost incomprehensible. A single powerful flare can equal the output of more than 10 billion hydrogen bombs, and the most violent coronal mass ejections can launch enough momentum to affect planetary magnetospheres across billions of miles of space. Signs are mounting that solar cycle 25 is distinct from its recent predecessors. Active regions persist for longer spans as they rotate across the solar disk, evidence of stronger field concentrations and enhanced plasma confinement. The butterfly diagram, which traces the shifting latitudes of sunspot emergence over time, shows that peak conditions have not yet arrived, leaving open the possibility that maximum intensity still lies ahead. Global connectivity across the solar surface has also increased, with coronal holes and high-speed streams opening pathways for magnetic interaction between regions thousands of miles apart. This creates conditions for sympathetic flaring, in which an eruption in one sector destabilizes distant regions linked by invisible magnetic threads. Inevitably, comparisons arise with the Carrington event of 1859, the most extreme geomagnetic storm ever recorded. During that storm, auroras flared as far south as the Caribbean, telegraph operators received electric shocks, and wires carried current even when disconnected from power supplies. Yet there are important differences between then and now. Today, space weather forecasting offers tools unimagined in the 19th century. Satellites may remain vulnerable, but many carry hardened electronics and redundant systems. Power grid operators are briefed with real-time forecasts that allow protective measures. Awareness alone transforms the risk landscape. Still, one must ask what would constitute evidence that solar cycle 25 is approaching a resonance saturation moment, a period when activity climbs high enough to challenge the resilience of our modern infrastructure. Indicators would include a sequence of X-class flares paired with high-velocity, Earth-directed mass ejections, overlapping impacts that merge into compound geomagnetic storms, and F10.7 flux values climbing to or beyond those of past maxima. Current observational assets provide unprecedented coverage. The geostationary operational environmental satellites monitor X-ray output and charged particle flux. The Solar Dynamics Observatory returns exquisite images of magnetic evolution in active regions. Ground-based radio networks track the passage of coronal mass ejections through interplanetary space, while magnetometers around the world record the reverberations of geomagnetic storms. As the period from October 19th through October 26th approaches, this global infrastructure will be vital in assessing whether the alignment of comet SWAN, the interstellar visitor 3I Atlas, and heightened solar activity produces signals of interaction beyond ordinary variability. Should electromagnetic coupling between comets and the Sun prove genuine, correlations in timing, directionality, or intensity could emerge. For the moment, practical risk assessments focus on the tangible. High-frequency radio blackouts on the sunlit side of Earth are possible if additional M or X-class flares occur. Such disruptions interfere with aviation and amateur radio communications, but generally cause no lasting damage. More concerning are geomagnetic storms that might drive auroras to unusually low latitudes, or in extreme scenarios induce currents strong enough to threaten transformers and trigger regional blackouts. Satellites may also be affected, suffering radiation damage or orbital perturbations from increased atmospheric drag. As solar cycle 25 continues its surge, the October convergence offers a rare natural experiment, a chance to examine whether apparent cosmic coincidences can amplify the drama of space weather. Whatever the outcome, the data will enrich our knowledge of how magnetic energy moves through the solar system, linking comets, planets, and stars in an intricate electromagnetic web. The Sun is rising toward a peak of activity not seen in years, and as it does, it reminds us that our lives unfold beneath the shifting moods of a star whose storms reach across the gulf of space to touch every corner of our world. Part 12. Cometary Resonance and Planetary Stress. In the dim borderlands where space weather meets seismology, a provocative idea has taken root, one that unsettles conventional thinking about the physics of earthquakes. This idea, known as the electroseismic storyline, suggests that disturbances in the electromagnetic environment of Earth, driven by activity on the Sun, might influence the timing of seismic events. It does not claim that solar storms cause earthquakes outright, but rather that they could nudge fault systems already on the verge of rupture, shifting the moment when stress is released. The concept deserves careful attention because it brushes against one of the most persistent and elusive goals in hazard research: the prediction of earthquakes. For decades, scientists have poured effort and funding into this quest, but prediction has remained beyond reach. Fault systems are complex, governed by microscopic changes in stress, fluid pressure, and material properties that decide whether tectonic strain is dissipated gradually or discharged suddenly in catastrophic failure. The official stance of the United States Geological Survey is blunt and unyielding. There is no demonstrated causal relationship between electromagnetic disturbances and earthquakes. This conclusion reflects decades of analysis, comparing global earthquake catalogs across multiple solar cycles and consistently finding no statistically significant correlation between the intensity of geomagnetic storms and the timing or magnitude of seismic events. Yet outside the mainstream, a chorus of alternative research continues to report correlations too intriguing to dismiss. Peer-reviewed studies have documented associations between anomalies in the atmosphere or ionosphere and the subsequent occurrence of large earthquakes, particularly in tectonically restless regions. These models fall under the broad heading of lithosphere-atmosphere-ionosphere coupling, or lake, which suggests that electrical and electromagnetic processes may play underappreciated roles in seismic behavior. The mechanism, as described, begins with the buildup of stress within rock formations. Laboratory experiments confirm that stressed rocks can generate electrical currents and electromagnetic emissions through mechanisms such as piezoelectric effects and charge separation. At the scale of major faults, such processes could theoretically send electrical disturbances upward into the atmosphere, eventually perturbing the ionosphere in ways detectable by satellites. In some cases, ionospheric anomalies have been reported hours or even days before major quakes. The more controversial step is to reverse this logic. Could external electromagnetic influences, pouring down from the ionosphere during geomagnetic storms, penetrate the crust and alter the electrical conditions of rocks already loaded with stress? Proponents argue that during intense space weather events, current systems in the ionosphere might couple downward, subtly influencing crustal conductivity and perhaps the timing of fault rupture. The difficulty, of course, lies in scale. Even the strongest geomagnetic storms induce currents many orders of magnitude weaker than the mechanical forces driving tectonic rupture. But complex systems are not always linear. They can harbor thresholds where small inputs, applied at precisely the right moment, trigger outsized responses. History offers tantalizing, if circumstantial, examples. The Tohoku earthquake of 2011 in Japan, one of the most devastating in modern history, occurred during a period of heightened solar activity. The Chiapas earthquake of 2017 in Mexico coincided almost to the day with extreme space weather surrounding the perihelion passage of the interstellar visitor Oumuamua. More recently, the Turkey-Syria earthquake sequence of February 2023 unfolded during elevated geomagnetic activity. None of these alignments proves causation, but collectively they underscore the challenge. Independent processes occasionally fall into synchrony, and the human mind struggles to distinguish coincidence from connection. Statistically, major earthquakes of magnitude 7 or larger occur roughly once per month worldwide, while geomagnetic storms of significant intensity strike perhaps once or twice each month during solar maxima. Overlaps are inevitable, and coincidence alone cannot establish a physical link. To test the hypothesis rigorously requires Bayesian statistical analysis, comparing global earthquake rates during periods of enhanced space weather against baseline rates in quiet times. Criteria must be clearly defined. For example, geomagnetic indices such as Kp values exceeding 6 for longer than 24 hours, or the presence of Earth-directed coronal mass ejections following X-class solar flares. Earthquake catalogs would then be scrutinized to see whether rates of magnitude 7 or greater events rise above baseline expectation. Such work must also account for natural clustering in seismicity, seasonal biases in detection, and the multiple comparison problem inherent in testing many possible correlations. Equally important is the matter of communication. Public safety depends not on speculative prediction, but on preparedness. The temptation to sensationalize potential correlations between space weather and earthquakes is strong, particularly when vivid coincidences seize attention. But science bears the responsibility to distinguish carefully between correlation and causation, between intriguing possibilities and established fact. The key message must remain clear. Preparedness culture saves lives. Prediction does not. Regardless of space weather conditions, seismic zones remain vulnerable, and the overwhelming majority of earthquakes occur during periods of entirely ordinary solar behavior. If space weather exerts any influence on seismic timing, it is at best a subtle modulation, not a predictive clock. As the October convergence approaches, with comet SWAN nearing Earth, 3I Atlas approaching perihelion, and the Sun itself entering a period of heightened activity, the global research community finds itself facing a rare natural experiment. The question is not only whether comets and solar storms might interact electromagnetically, but also whether those interactions could ripple further, influencing processes deep within Earth's crust. If genuine coupling exists, we might observe a faint but measurable uptick in seismic activity during periods of intense space weather. If not, the coincidences will fade into the background noise of random overlap. Either outcome represents progress. If no link is found, the boundaries of seismology and space physics will be clarified. If a link emerges, even faint, it will force a reconsideration of how energy moves across the boundary between Earth and sky. For now, the hypothesis rests in that uncertain place where speculation meets curiosity, awaiting data to confirm or deny. And in that waiting we glimpse the deeper truth, that we live on a restless planet orbiting a restless star, and that the invisible threads of electromagnetic energy that weave space and Earth together may hold secrets we have only begun to suspect. Part 13 Mars, 3I Atlas and the Shadow Alignment. While Earth-based observers struggle to catch even a fleeting glimpse of 3I Atlas through the overwhelming glare of the Sun, Mars now finds itself in the privileged position of holding front-row seats to one of the most consequential interstellar encounters in the history of astronomy. The orbital geometry unfolding in early October places the red planet in a vantage point so ideal that it seems almost designed for study. From this position, Mars can monitor the mysterious visitor as it approaches perihelion, potentially developing the kind of spectacular coma that could transform our understanding of how interstellar matter behaves when immersed in solar radiation. The orbital mechanics behind this configuration reveal a picture of remarkable precision. On or around the 3rd of October, 3I Atlas will pass within roughly 30 million kilometers of Mars, about 0.19 astronomical units, or close to 80 times the distance separating Earth and its moon. Though such a gulf is vast in human terms, it places Mars-based instruments well within range for detailed spectroscopic analysis, dust detection, and measurements of electromagnetic interactions between the interstellar object and the solar wind. This encounter carries extraordinary weight because it may represent humanity's best chance to study an interstellar body during its most active stage. Oumuamua, discovered in 2017, remained strangely inert as it tumbled through the inner solar system, while 2I Borisov in 2019 developed only a modest coma. 3I Atlas, however, hints at far more dramatic activity as it nears the peak of solar heating, raising the possibility that it could erupt into a full-fledged cometary display. The European Space Agency has already recognized the opportunity and announced that multiple spacecraft orbiting Mars will be redirected to observe the interstellar visitor. Mars Express, a mission that has circled the red planet since 2003, carries high-resolution spectrometers capable of identifying the chemical fingerprints of any emerging coma. The ExoMars Trace Gas Orbiter, originally designed to analyze Martian atmospheric chemistry, may detect exotic volatile compounds sublimating from the nucleus of 3I Atlas. These instruments will operate at the very moment Earth itself prepares for the closest approach of comet SWAN on the 20th and 21st of October. The near simultaneity of these encounters creates a rare comparative experiment. One object from the distant Oort cloud of our own solar system, the other a wanderer from beyond the heliosphere, both exposed to similar radiation environments within weeks of each other. Such a pairing offers a natural test of composition and structure. SWAN, born from the same primordial disk that gave rise to the Sun and planets 4.5 billion years ago, should display the familiar volatile content and dust properties of solar system comets. 3I Atlas, by contrast, carries the chemical and electromagnetic imprint of an entirely different stellar nursery, potentially bearing exotic materials never before studied inside the heliosphere. Theoretical scenarios multiply when scientists consider how a large outgassing interstellar body might interact with the solar wind environment around Mars. The red planet, with its thin atmosphere and only vestigial magnetic field, offers a plasma boundary that is unusually sensitive. Should 3I Atlas release a substantial cloud of ionized gases, it could locally alter the Martian plasma environment in ways that echo the spectacular encounter of comet-siding spring in 2014. That Oort cloud visitor swept so close to Mars that its coma enveloped the planet, triggering the most intense meteor storm ever recorded there. NASA's MAVEN spacecraft observed metallic ions deposited throughout the Martian upper atmosphere, disturbances in the ionosphere that lingered for days, and heating of hundreds of degrees. The demonstration was clear. Comets, even brief passers-by, can deliver enough energy and material to alter planetary systems. If 3I Atlas proves richer in volatiles, its influence could be even more pronounced. Yet its value lies not only in planetary effects, but also in what it may reveal about interstellar origins. If the object carries embedded magnetic fields or distinctive plasma behaviors from its natal environment, Mars-based instruments could provide humanity's first direct measurements of how interstellar matter interacts with the structured magnetic architecture of the heliosphere. The encounter also carries symbolic resonance within the broader October convergence. Although invisible from Earth due to its proximity to the Sun, 3I Atlas is at that same moment aligned with heliospheric current sheet layers that comet SWAN is also traversing. Both objects, despite their radically different origins, find themselves embedded within the same electromagnetic structures, just as solar cycle 25 climbs toward heightened activity. The possibility arises, however faint, that the combined plasma output of two large active objects traveling through the same sheet layer might create perturbations detectable as anomalies in the heliospheric circuit. The notion is speculative, but instruments such as Parker Solar Probe, currently measuring magnetic fields and charged particles near the Sun, may hold the sensitivity needed to test whether such multi-object coupling produces measurable signatures. The challenge, as always, is disentangling genuine physical effects from the natural turbulence and variability of solar plasma. For observers stationed at Mars, the priorities are clear. Document the composition of 3I Atlas, track its outgassing behavior, and search for electromagnetic signals that distinguish interstellar material from solar system matter. Spectroscopy could uncover hypervolatile species absent in familiar comets, while dust sensors might capture grains with mineralogies alien to the solar system. Radio or plasma detectors could log wave emissions tied to interactions between the comet's coma and the solar wind. The timing of this sequence offers an unfolding chain of observations. Mars will deliver reconnaissance data in early October. Earth-based observers will watch SWAN in mid to late October, and the Sun will meet 3I Atlas head-on when it swings through perihelion on the 30th. Each stage builds on the previous, offering a progression of insights into how different kinds of cosmic wanderers respond to the same radiation environment. Whether the outcome is a dazzling interstellar display or a confirmation that even alien comets follow familiar physical laws under solar heating, the knowledge gained will be transformative. The red planet, often imagined primarily as the next frontier for human exploration, now takes on another role as an astronomical observatory, positioned perfectly to watch an emissary from beyond the stars. As 3I Atlas hurtles toward its moment of maximum exposure, Mars stands as witness, ready to capture the secrets this enigmatic traveler may carry from its distant birthplace in the galaxy. Part 14. The Great October Window. The calendar turns toward a week, unlike any other in recent astronomical memory. 7 days of choreography so precise that it threatens to blur the line between coincidence and causation. From the 19th of October through the 26th, the heavens align in ways that could reveal hidden pathways of electromagnetic energy across the solar system, or else remind us that even the most breathtaking alignments are nothing more than the mathematical inevitabilities of orbital mechanics unfolding on the vast canvas of interplanetary space. The stage opens on the 19th, when comet SWAN continues its march toward minimum Earth distance. Nearly a month will have passed since its sudden eruption of the 26th of September, enough time for shockwaves and coronal mass ejections from the solar flare of the 28th to traverse the 40 million miles between the Sun and the comet's orbit. If there is truth in the idea of electromagnetic coupling between comets and solar activity, this is the period when the first faint signatures may appear. Telescopes across the globe will be turned skyward, lenses and cameras waiting to capture signs of sudden transformation. A disconnection of the tail, a surge of brightness, or structural rearrangements, all familiar hallmarks of comets caught in the grip of solar wind disturbances, could announce that SWAN is more than just an icy wanderer. 2 days later comes the fulcrum of the entire convergence. The 21st of October represents the mathematical center of the alignment, the point at which 3 separate celestial events overlap with uncanny precision. On this night, the moon withdraws into its new phase, extinguishing its light and leaving the sky at its darkest. The absence of lunar glow provides optimal viewing conditions just as SWAN makes its closest pass to Earth, a mere 0.2606 astronomical units, roughly 10 million miles. At the same time, 3I Atlas, still hidden within the Sun's blinding glare, moves inexorably toward its perihelion of the 30th of October, perhaps building a coma so immense that it could reshape the local solar wind environment. This triple coincidence, new moon, closest approach, and approaching interstellar perihelion, constitutes the very heart of the convergence window. The moon's retreat is not just a poetic alignment, it is a practical gift. With darkness restored, even subtle fluctuations in tail morphology or coma brightness can be detected by patient eyes and sensitive instruments. Amateurs scattered across deserts and mountains will stand shoulder to shoulder with great observatories, their digital cameras and long exposures weaving a global net of vigilance. Every flicker of SWAN's form will be documented, compared, and analyzed in search of evidence that comets and solar storms dance to an unseen rhythm. While the night sky offers the visual stage, a chorus of instruments will hum in constant vigilance. The geostationary satellites of the GOES constellation will track solar X-ray flux, listening for the crackle of flare activity. The coronagraphs aboard the solar and heliospheric observatory will map the birth and trajectory of coronal mass ejections, watching for plasma clouds thrown into regions of space suspiciously close to SWAN or Atlas. Radio telescopes will strain to catch whispers from the ether, the deep rumble of Type 2 bursts, announcing shockwaves sweeping through the solar wind, and the sharper tones of Type 3 bursts, signatures of electrons whipped into acceleration by magnetic reconnection. Should coherent emissions appear that tie comet positions to solar active regions, such data would constitute the strongest hint yet of electromagnetic bridges spanning millions of miles. On Earth's surface, magnetometers embedded in a global grid will trace the subtle quivers of our magnetic field. Their aggregated signal, distilled into the planetary KP index, will reveal whether geomagnetic unrest accompanies the days of convergence. Elevated readings could suggest that comets are not simply passive bodies but active participants in the orchestration of space weather. Yet for all this anticipation, caution reigns among professional forecasters. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center reminds us that while probabilities can be inferred from solar active region complexity, the precise timing of a flare remains beyond our reach. Statistical models offer forecasts, but certainty lies forever just outside the grasp of current science. The October window, therefore, must be approached as both promise and restraint, a chance to glimpse the extraordinary, tempered by the knowledge that the ordinary is far more likely. Mainstream physics expects SWAN to behave as comets do tails reshaped by gusts of solar wind, occasional disconnection events if a coronal shockwave sweeps past, but nothing more. The speculative hypothesis that comets embedded in the heliospheric current sheet might modulate solar activity through plasma loading makes predictions more daring. Timing correlations between flare production and cometary behavior, coherent radio emissions linking distant positions to active regions, anomalous particle populations tracing back to cometary plasma. Safety concerns anchor the excitement. High-frequency radio blackouts could disrupt aviation communications on the daylight side of Earth if solar flares intensify. Navigation satellites might register positional errors. Power grids could experience induced currents, and aurorae might spill into skies unaccustomed to their glow. Severe outcomes remain unlikely, but not impossible. In the worst case, transformers could fail, satellites could falter in their orbits, and modern systems could briefly remember their dependence on the moods of the Sunday. Into this delicate balance steps the global community of citizen scientists. Never before have so many cameras, telescopes, and networks been poised to record a comet at closest approach during skies darkened by new moon. With standardized timing protocols, careful logging of equipment, and collaborative sharing on digital platforms, amateurs can generate data of surprising scientific value. Images gathered from multiple continents could reveal changes too rapid for single observatories to detect, weaving together a time-lapse of cosmic interaction across the span of the Earth itself. As the 26th of October closes the curtain on this 7-day experiment, humanity will hold in its hands a trove of observations. The data may reveal correlations that hint at hidden electromagnetic coupling, or they may show nothing beyond the familiar signatures of comets buffeted by ordinary solar gusts. Either way, knowledge advances. If coincidences remain coincidences, science will stand affirmed in its restraint. If patterns emerge that exceed randomness, then a door opens toward a deeper understanding of how energy and information cascade across the solar system. The convergence window thus becomes not just an astronomical event, but a philosophical test, a reminder that curiosity thrives at the boundary where skepticism and wonder meet. The 19th through the 26th of October offers no guarantees. It offers only the chance to look, to measure, and to decide whether the universe has revealed a hidden harmony or simply reminded us of the power of coincidence. Either conclusion honors the pursuit of truth, For in the act of watching closely, we enlarge the circle of human knowledge, binding our small world more tightly to the vast and restless cosmos. Part 15. The Meta-Pattern, Consciousness, Resonance, and the Living Cosmos. As our investigation draws toward its climax, the questions before us stretch far beyond the mechanics of comets, solar flares, and electromagnetic coupling. The October convergence, whether it proves to be choreographed by some hidden cosmic order or nothing more than coincidence, shines light on something deeper: the nature of pattern recognition, the discipline of scientific inquiry, and humanity's fragile yet determined relationship with the cosmos that has always surrounded and shaped us. From nova photons racing across interstellar gulfs at the speed of light, to cometary plasma clouds streaming from ancient nuclei at 30 kilometers per second, from coronal mass ejections carrying billion-ton payloads of magnetized plasma, to the faint electrical currents shimmering in Earth's ionosphere, all of these events reveal themselves as expressions of a single interconnected plasma ocean. It is an ocean that stretches from the nuclear furnaces of stars to the thin atmospheres of planets, binding environments across scales that challenge imagination. In this systemic view, the solar system is no longer a collection of independent bodies drifting along Newtonian orbits. Instead, it emerges as an integrated electromagnetic machine, a living circuit where information and energy ripple through invisible wires of plasma and magnetic field lines. The sun, planets, comets, and interstellar visitors become nodes in a vast network whose feedbacks and thresholds connect processes that appear unrelated when studied in isolation. Yet, this perspective also demands humility. Human beings are pattern-seeking creatures. Our minds weave narrative threads that transform random alignments into meaningful stories of purpose and design. The challenge before science is to distinguish genuine signals from the static of coincidence, to test whether correlations hold under rigorous scrutiny or dissolve into the dust of imagination. It is here, in the tension between wonder and skepticism, that discovery is born. The enigmatic arrival of interstellar wanderers like 3I Atlas expands this conversation in unexpected ways. Each such visitor carries within it the story of stellar nurseries, galactic chemistry, and the uncharted spaces between stars. They are cosmic messengers, testing the boundaries of our models and sometimes demanding entirely new frameworks of explanation. Should 3I Atlas prove to carry hypervolatile materials or dust grains with properties unlike any seen in the solar system, then our most basic assumptions about comet formation and interstellar environments will need to be rewritten. The humility clause of this investigation insists that we acknowledge scale. The Sun contains more than 99% of the solar system's mass and generates magnetic fields powerful enough to bend cosmic rays across billions of miles. Against such immensity, the influence of a comet, even a large and active one, seems negligible. Any hypothesis of comet-to-sun feedback must operate in this intimidating energy gradient. Yet, history in plasma physics warns us not to dismiss small players outright. Instabilities born on microscopic scales can cascade upward, triggering reorganizations that reshape entire systems. Sometimes the smallest push, delivered at precisely the right moment, can release stored energy in ways disproportionate to the initial disturbance. The search for such threshold effects demands careful observation and patient analysis. If weak electromagnetic coupling between comets and solar activity exists, it will not declare itself through spectacular single events. It will emerge only as subtle timing biases, detectable only in large statistical samples that cover many solar cycles. Individual alignments, like those of September and October, may remain ambiguous, enticing, but inconclusive. What is needed is systematic, long-term comparison across dozens of events. Here, citizen scientists may play a role as crucial as that of national space agencies. Mainstream observatories often focus on well-established research programs. Speculative hypotheses, like comet solar coupling, may attract little institutional time or funding, but thousands of amateurs, equipped with digital spectrometers, sensitive cameras, and the determination to contribute, can form an observational net wide enough to capture the faint signatures of interaction. If organized into coordinated campaigns during convergence periods, their collective data could reveal patterns invisible to single instruments. This democratization of astronomy turns every backyard telescope into a potential witness of subtle cosmic processes. The October window, centered on the 21st, embodies this tension between possibility and restraint. On that night, SWAN will sweep past Earth at just over 10 million miles while the Moon hides in darkness, offering ideal conditions for observation. 3I Atlas, cloaked behind the Sun, moves toward its own moment of closest approach, perhaps building a coma, unlike anything we have yet seen from an interstellar visitor. Meanwhile, the Sun itself grows restless, its cycle more active than predicted, releasing flares and coronal storms with increasing frequency. Whether these alignments represent physics or chance, they offer a natural experiment of rare clarity. The deeper beauty of this moment lies not in what the outcome proves to be, but in the process of inquiry itself. Science is strongest when it allows room for imagination while insisting on discipline. The questions asked here about coupling, feedback, thresholds, and coincidence carry meaning because they are testable. They challenge us to look, to measure, to compare, and to be willing to accept whatever the evidence reveals. If no correlation emerges, we learn that coincidence is enough to explain even the most dazzling alignments. If faint correlations persist, we open a new chapter in understanding the solar system as a responsive electromagnetic whole. The meta-pattern that surfaces from all of this is perhaps the most humbling of all: consciousness itself. The fact that human minds can contemplate the behavior of photons, plasma, and magnetic fields, that we can imagine connections across millions of miles and millions of years, that we can test those imaginings with instruments and statistics, this is itself a cosmic phenomenon. Intelligence, observing the cosmos, is part of the cosmos observing itself. Whether the October convergence proves to be choreography or coincidence, it undeniably reveals the power of curiosity to transform distant astronomical alignments into opportunities for deeper knowledge. The final verdict will emerge not from speculation, but from the data streams that flow from satellites, ground-based telescopes, radio arrays, and the photographs captured by amateurs in clear dark skies. And yet, regardless of the verdict, something vital has already been achieved. The very act of framing the question, of recognizing the possibility of hidden connections and daring to test them, affirms humanity's place in the ongoing dialogue between order and chaos, between wonder and skepticism, between imagination and evidence. The universe, vast and restless, will continue to surprise us with its beauty, its violence, and its occasional suggestion of deeper harmony. But in the end, it is not the cosmos that provides meaning, it is our determination to look, to question, and to understand. That is the true climax of this investigation. For in our quest to map the hidden flows of energy that bind comets, stars, and planets together, we discover the even more astonishing networks of meaning that bind us to the universe as conscious participants in its unfolding story.